Hello, everyone. Welcome to another StatiCa webinar. Today, we will speak about another topic for, let's say, beginners with StatiCa connections, and it will be about shear connections. So, welcome again. My name is Jana Kadirova. I'm a product engineer at StatiCa, and I've been working here for more than 4 years, I think. And I will present today's topic. You are welcome to ask different questions. Please use the GoToWebinar panel for questions because you are muted for the practical reasons. But I have my colleagues with me who will try to answer your questions during the webinar. And if there are more questions than we are able to handle, we will answer them after the webinar by email. Today's webinar is another part of, let's say, special summer series for beginners. It's called Tackling StatiCa Connection. It's a series of 5 short webinars. It will take about 30 minutes approximately. And we wanted to focus on real beginners. If you are new to StatiCa, you can learn something very quickly and easily. And of course, you can watch the webinar even if you are advanced to repeat, or maybe you will find out something new for you as well. So we are just in the middle of the series. In the previous parts, Adam introduced the very basics of the software, like installation, license, activation, and opening and starting new project. And last time, my colleague Janko spoke about moment connections. What are their specifics, how to model them effectively, and also important topic about the loads on such connections. And he also presented a little bit of a stiffness analysis, how to use the equilibrium for loads, and also our new pre-design feature. You can look forward to seeing another 2 parts in the future. It will be about complex joints, and last part about beam links. So in today's topic, I will continue in what Janko started last time, because shear connections are just another group of connections next to the moment ones. It's said that they are generally the most commonly used type of connection because they are probably cheaper and easier to construct. The other the little disadvantage is that they do not provide lateral stability for the structure. So therefore, there must be added some bracing system for or diagonals. We will have a look at special templates that we have for shear connections. We will speak about how to load them correctly and how to correctly define the load force position, and when is it necessary to change the model type. In the end, we will have a very short look at the stiffness analysis as well. Great. So let me switch off the camera so that we will see the presentation in full, and after a short while, we'll start a demonstration. So shear connections are next to moment connections, another big group, and the typical characteristics of it is that they transfer the shear force only. So no bending moment or a little bending moment. They can be loaded in a pure normal force load, so we call them tension joints, or pure shear loading, or a combination of that. A special group of shear connections are the pinned connections, which also transfer only shear force and cannot resist any bending moment. So they can really rotate freely. or at least they seem so. I have some examples of them in the figure, so you can see some fin plates or shear tabs, as we call them, or some cleat connections, or a typical example of an pinned connections in anchorings. So let's start how we can easily model them. I will just repeat what Janko mentioned before. So very quickly, we have a connection wizard for starting a new project with a large library of different connections, and we have special groups for shear connections there as well. Another possibility is to use the right-click mouse button where another library opens, or our template manager, let's say. And the last option is to use our propose function. Maybe it looks difficult to understand why we have so many ways how to open the library. So let me just mention that the templates manager, the old way, will be closed in some next versions, and the propose, which is now still in beta regime, will be the main library of your templates, or generally of any templates. And of course, we have you don't have to use any of the template from the library, but you can create your own connection using our library of operations. I will present them as well. We have a special operations for gusset plates, fin plates, or shear tabs, connecting plates, cleat or angle connections, and shear end plates, and many more. Okay, so now let's have a look in the application directly, and let's start a new project. So I will just quickly show you the connection wizard for starting a new project. In the first, let's say, part, you can select the different class of the connection, different topologies, and in the third column, you have different designs already. Under the moment connections, we have different shear connections grouped together. So you can always have a look at it and so on. The other, also, sorry, we have a special class for the truss connections, which are always shear. So all of these are special type of shear connections. If you do not want to use any of these templates, or you are not sure, you can, of course, use the blank connection and create such a blank project. So let's create a new one. So in such a case, I will have there only members with no loads and no operations. So as I mentioned before, I can use the right mouse button and open a connect to option, select the other member, and a library opens. In such a case, we do not group or differentiate between the moment and shear connection, so the user has to define or decide himself or herself. You can see that easily a fin plate operation has been applied. Of course, I can adjust all the parameters here if I want to. Let me now clear the operations, because I want to show you the template manager. So if I open the apply button, again, a library of different types of connections that are applicable at this topology opens. Again, I can apply a fin plate. It looks a little bit different. There are two operations. I have a stiffeners and a fin plate. Okay, let's clear it again, because I will show you the propose beta function, which in a short while will be the main library of templates. And you can see that for selected topology, again, I have many templates, and in the future, I will be able to save my own templates or company templates as well. So let's apply a fin plate again. And you can see it's there. I have one operation. Okay, so now we will try to play a little bit with the fin plate so that you can see what is possible. You can, of course, switch between the bolted and welded one. I can change the position to from rear to front. So let's leave there the bolted option. And I can, of course, change the bolt type, and I can add another rows or columns of bolts. I can change the spacing and so on. At this moment, the reference line for the bolt spacing is a central line, which is defined here. I can switch this option to top of steel if you are more familiar with such an input. And now my new zero is a top surface or the edge of the beam B. So now you can add again new row of bolts. I can add another column or maybe even two of them like this. Sometimes I want to have some uneven distribution of bolts, and I will show you how you can reach such configuration. So if you want to shift or move the bolt in a specific position, I can do it via our editor. So the editor can be opened either with a right mouse button, clicking on the fin plate and selecting editor, or in the top ribbon above the parameters grid, there's editor as well. So let's open it, and you can see I have a bolt grid here. If I want to edit it, I have to explode it. And now I can do different operations. I can, for example, delete some of the bolts, or I can move the bolts into a specific position, like this, for example. Okay, so now we can calculate the project, but before I have to input some load. For the shear connection, it's important to realize that there is no bending moment acting, or there shouldn't be, or at least a little slight one, because otherwise the connection, if you considered the connection to be shear in your global model, then the internal forces should correspond to that. So I have calculated the project, and let's have a look at the results. So at the first sight, it looks okay. Let's open some more detailed result, and let's have a look at a mesh and deformed shape. And now you can see that it deformed in a really strange way. I suppose you expected that it will turn the other way. So why did that happen? I will switch back to my presentation to explain this phenomenon a little bit. So we have to realize how to correctly define the load and what does it mean. So this is the real shape of the joint. Let's say it's a cut part from the global model that is modeled in StatiCa connection. In the 3D FEM model, it's represented by 1D members or their axis. In StatiCa connection, we define the loads at the node. So at the point where these axes intersect or where the node is defined. This is an example of a connection where a combination of shear force and bending moment is defined. And because we need to apply, or we want to have the distribution of forces along the whole, let's say, cut part of those members, we need to, let's say, extrapolate them somehow from the node farther. So we assume that the shear force is constant, while the bending moment has a linear distribution. The slope is defined as its tangent is equal to the shear force. So for such a general connection where bending moment and shear force is defined, you can have such distribution. You can always display the bending moment in StatiCa connection. For the hinge, where we do not input any bending moment, the distribution looks like this. So at the node, we have a 0 bending moment. So this is for the, let's say, frame model. But in reality, the position of the real hinge is somewhere else. It's not at the intersection of axes, but due to the sizes of members, the hinge is shifted a little bit to different position. So you can see that for a hinge, which is located a little bit farther from the node, there is already a slight bending moment acting. So what we have to do now is either change the global model and put the real hinge into a correct position where we expect it really will be, or we will make a little trick in StatiCa connection and we can shift the position of a shear force into the centroid of the bolt group. So at the left figure, you can see the standard default configuration where the forces act in a node, but we have a bending moment at the place of the fin plate. And this bending moment caused the upward deformation. Now we can do a change in the model and shift the shear force into a position of bolts so that we have 0 bending moment there. So let's get back to my model. I will switch back to design, open the B member and shift the force to bolts. Now let's calculate the project again. Let's have a look at it in results. And okay, now it deforms downwards, so that's fine. Next, I want to show you another thing in the editor. So I will just copy this project. And maybe you have noticed that in the editor, there's also a possibility to change the whole shape from the circular one to the slotted one. So I can do it like so, apply. In a transparent view, you can see that the holes are slotted. If I will start the calculation now, I will wait for results. And you can see that there's already some problem in the iteration process. And in the end, I will find out that the calculation is unstable and cannot run anymore. So I will not have any results. Yeah, you can see that the analysis did not run. This is due to the reason that with the slotted hole, we released the vertical degree of freedom. So at the moment, there's nothing holding the beam in the vertical direction. Okay, so I will open the operations and I will add a cleat that will transfer the shear force. So operations is a set of different predefined let's say, little templates that you can apply on your connection. I want to apply a cleat now, and I will put the cleat on the bottom flange of the B member. Sorry, bottom one. I want to have only one, like this. I will change some bolt spacing so that it's only like this. Okay, and now if I calculate the project, the cleat will transfer my shear force. Let's have a short look. Yeah, you can see. If I open the bolt forces and I will open the results for bolts, you can see that there is no vertical component of the resultant force. Okay, great. So speaking about the operations, I want to show you that we have different types of operations. Therefore, I will copy my project, go back to design, and clear it so that I have only members here. And if I want to apply any operation, I can open this step in the ribbon. And we have different kinds of operations. Generally, we can say that the top ones are more specific. So you can reach your design with only one operation. Let's say I want to apply, I can apply a gusset plate or connecting plate, and this will be all modeled in one go. If you want to do something more specific, we have also operations for that. They are very general, like general plate, general cut, general bolt. And with these operations, you can really model your custom design. So let me just show you that I can make a special variation of the fin plate on my own with the general operations. I will cut the B member by C, but I don't want to weld it. And I will put there a 10 millimeters gap. And now I will add a stiffening plate, which is this operation. I will relate it to member B, to its web, and it will be a doubler of the web. And I want to have both of them. Okay, now I have to change the sizes like this, and I will switch off the welds. I can of course change the thickness and weld thickness and so on. Now I want to weld these plates to the bottom web of the column, so I will use a cut of plate operation. I will select the plate, and to be cut by C, you can see that it's already here. I will only switch the weld to one side. And now I will copy the operation once more and change the cut plate to the next one and switch the weld to the other side. Okay, I have two fin plates from both sides of the web of the beam, and now I want to bolt them together. I will add a general bolt operation. The bolt will go through 3 plates, so I will change the item count to 3. And with this picking tool, you can easily pick your plates. The second one, I will switch it to member and select it in the scene. And the third one is already selected. You can see that all 3 plates change the color to brown. I can define my new 0 for the bolt and put there a new bolt spacing. And that's it. So we can see that you can make very custom geometries with these general operations. Okay, so in one of the last example, I will start a new project here, and I will select this connection, this moment connection, where I will try, or I will add a diagonal. So let's open a new template. You can see I have two operations here. I have a stiffeners and a cut, and I will add a new member. I can do it here in the top ribbon. I can rename it with the right mouse button, but let's leave it like it is. I will change the cross section to some circular one. Let's use this one, for example, like so. I will switch the geometry type to end it and defined a pitch, -50. Okay, like this. Now I want to add a connecting plate that will connect the diagonal to these two beams. The operation has been applied, but to a wrong member, so I can either select it, change it in a drop-down menu, or select the pick tool and select it in a scene. So now it's all right. It has been related to C member, and I will also add another related member to be the B member. And you can see that the plate, or the gusset plate, has been already welded to these two beams. Now we only need to change the size of it. So let's put there 120 and 150 in depth. And I will shift the position of the connection a little bit farther. And I will change also the size of the connection plate. You can also change the shape of the cap plate and so on. All the parameters are adjustable. I can, for example, put there a larger bolt. I can add another bolt, or I can shift them. You can also see that there are some clashes in the design, that these two plates intersect, and also on the other side I have some clashes. So I can get rid of them by applying special operations in an editor. So again, I can go through the 3D scene, open an editor for that, and let's apply a bevel at the gusset plate. These highlighted edges are the welded ones. So I want to add a bevel 40 and 45 at the second apex. Okay, and now that's it. For the other side of the connection, for the tongue, let's open the editor and let's put there a rounding. And I want it to be at the edge, or at the apex of 1 and 2. And it's been rounded as well. Great. Now I will just apply some axial load there to start the calculation. And we will have a look at the results. So at the first sight, it looks fine again, but I always recommend to open also the detailed results and the deformed shaped. And you can see there's something wrong. The model doesn't look very well. So why is this so? I will switch back to my presentation. And I have 2 slides about another important thing that you need to know when modeling shear or pinned connections in this case. So for pin connections, we have to change the model type because the pin itself doesn't have any rotational stiffness. It's usually holding only on one bolt, and this bolt doesn't provide any restrictions in rotation. So therefore, the model after the analysis looks like this. It's unstable. If we change the model type to be free in rotation, it means it will hold only the normal and shear forces. We will get the correct results. So let's go back to design. I will go into M3 member and I will switch the model type to the correct one. In the 3D scene, it's represented by this red cross, this boundary condition. Let's start the calculation again. And we will see that the results now are correct. And it is. The diagonal acts in tangent and it doesn't rotate. Okay, great. So in a very few minutes, because we are now behind the time. So if you are not sure whether your connection behaves more like a rigid connection that provides a lot of rotational stiffness, or it's more pinned, or somewhere in between, you can always run the stiffness analysis in StatiCa connection. For that, let me select, for example, the node number 2. I have this connection, and probably for our purposes, I will turn off the slotted holes back to the normal ones. And if I want to change the analysis type, you can do so in the top ribbon on the left side. Select the ST for stiffness analysis. Okay. And now for the stiffness analysis, we have to load the connection in bending by the bending moment, so we can see how it behaves in while loaded with the bending moment. Now I can start the calculation. It will take a little while, and after that I will see the diagram of the response on this bending moment and how it rotates. And based on the classification, which is defined by the used standard, you will see that the connection will be classified either as pinned or as rigid or something in between. So let's open results. I have rotational stiffness, and you can see that this is not a pure pinned connection. It's already semi-rigid. It has a slight rotational stiffness, and you can get the value of it that can be used in your global model. If you are interested in finding out more about the stiffness analysis, we have a special documentation for that. We have made many webinars on this topic as well. So that's all from my demonstration and basically all from the content of today's webinar. I want to mention or emphasize several few things before we end. The first one is that we have a special online platform for educating the engineers and our users how to correctly use our software. It's called StatiCa Campus. There's a special course which is called Theory and Practice of Steel Connection Design. You can get a certificate there. If you want to find out more, please go to our website, ideastatica.com/campus. You can go through the first, I think, 3 or 4 chapters for free, and the course is in English. Next time, I invite you to join our webinar that will be focused on more complex joints. My colleague Sasha will present such a beautiful connection and how to model it. And in the third part, in the last part, we will have a look at BIM links, how IdeaStatica communicates with your finite element tools or CAD tools, and how to get most of the workflows there. Thank you very much for your attendance today. After we finish the webinar, you are asked to fill a short survey and give us some feedback on how you like the content and the webinars you have just seen. We will provide you also by the recording. It will be available on our YouTube channel or in our support center. If you want to try IdeaStatica Connection, you are very welcome to download a trial version for 14 days and for free. And of course, we have many documentation, many tutorials, webinars, and so on. Please go to our support center to find out more. Again, thank you very much. Have a nice summer and goodbye.